So today's lesson is on our second out of our 3 bonding types, ionic bonding. So you'll need your notes handout today. You will probably also want to have your colored periodic table out today that shows the difference between metals and nonmetals. And then we're eventually going to unpack and talk about naming ionic compounds and writing formulas on ionic compounds. I'm not going to talk too much about this stuff at the end of the video today because most of the naming and writing formulas we are going to really dive down deep into for probably an entire week or maybe even more, because it does take a little bit of time and practice. But we are going to kind of have this out today as I do a little bit of an intro lesson on what it means to name or write formulas for my ionic compounds. Also, keep in mind, we remembered that our polyatomic ions, some of them, the ones with the negative charges, act metal or act non-metal-like. And then this guy down here, that positively charged polyatomic ion, ammonium, he acts metal-like. So they are potentials here in ionic bonding. So as a review, though, we are done talking about metallic bonding. Metallic bonding is like a little bit of a blip on the radar in my 3 types of bonding. We got a lot to unpack here with ionic bonding, and we even have a lot more to unpack with covalent bonding, which is why it gets its own unit. So ionic bonding, remember when we did our intro handout? We did the colors, right? Metallic bonds, they were all metals, right? The sea of electrons, the electrons delocalized. Ionic bonding, you guys, I got one of each, right? I've got my metals and my non-metals. So on our notes handout today, up here at the top of our notes heading, we're actually going to color the first half of this header red. Once again, red represents my metals. And then the second half, we're going to color blue. And the blue represents my nonmetals. Now, when it comes to naming and writing formulas for ionic compounds, the metal representative is always alluded to first or written first, which is why when we're doing our headings, I'm always going to put the red metal category first. Okay, so let's get into our lesson for ionic bonding and see what that is all about. Well, first of all, let's go back. The name's ionic bond, taken, not shared. So we wrote in our intro notes that ionic bonds transfer their electrons. They do not share like my covalents. Okay, and remember my atoms down here says, I'm about to lose an electron. Are you sure? Boom, I'm positive. Classic joke. I feel like I say it all the time, but it's still funny to me. And it's probably going to help you remember how cations are formed. Okay, so ionic bonding, y'all, I'm made up of one of each of these things. I'm made up of a metal, which we know form positively charged cations by losing their electrons, and nonmetals, which are formed by negatively charged, which form negatively charged ions by gaining. So ionic compounds are composed of a cation, which is a metal, and an anion, which is a nonmetal. Cations lose electrons. Example for that is sodium with a +1 charge. Makes sense that sodium makes a +1 charge because he is in group 1. And anions are ions that are negatively charged because they gain their electrons. An example is of chlorine. He's in group 17 with the other halogens. Yes, he makes a -1 charge because he gains an electron. These two guys could totally form an ionic bond together. Okay, we got our headings now, just like when we did a metallic bonding, we had a what happened. So here we're going to have a what happened for ionic bonding. So electrons are transferred from the metal to the nonmetal in order for both to achieve a stable octet and lower the potential energy of both ions. Once again, lowering the potential energy is a fancy way of saying we're calming everybody down to be in a more zen and calm state. Okay, I'm lowering kind of my anxiety. That's what atoms like to do. Lowering their potential energy makes them feel better and more stable. Okay, so achieving a stable octet actually does that for the atoms. So we see sodium, he is losing his 1 valence electron. It is just not being lost into the atmosphere. It is being lost and gained by chlorine, which is super exciting. Now I have a positive sodium cation and a negative chloride ion. And y'all, positive and negative. I think I know what's happening here, you guys. Okay, but let's talk about why this happens. Like, how come I know one element's going to transfer an electron to another? Well, you guys, remember our electronegativity trend? This actually happens. This transfer of an electron happens because the 2 atoms involved have a large difference in electronegativity. So as a reminder, our electronegativity trend here, It increases growing from left to right until I hit the noble gases. They do not have any electronegativity, which is probably why we're not going to involve them in our whole bonding lesson here. And then it also decreases going down a group, or it increases going up a group. So this corner over here with fluorine has my highest electronegativities on the periodic table. Over here, down here in the bottom corner where francium has my lowest. So I think we talked about last unit that metals, meaning this side of the staircase, tend to have lower electronegativities than my non-metals, right? Non-metals have high, metals have low. Okay, when you are further away from each other on the periodic table, we would expect a larger and larger and larger difference in those electronegativity values, right? So we know electronegativity is the ability for an atom to want to attract electrons in a chemical bond. Well, y'all, if I got somebody over here, a non-metal who's like super electronegative, he wants to gain electrons badly, and I got somebody else down here who is like, I do not care, I have really low electronegativity, what ends up happening is the bond is created an ionic bond from that transfer of electrons. So what is attempting to happen first is that you have atoms that are trying to share electrons, which they do if they're covalent bonds, which we'll talk about next unit. But if one atom, this guy over here, wants those electrons so much more, high electronegativity, that non-metal, more electronegative atom is going to completely steal those electrons from the less electronegative metal atom. So the more electronegative atom pulls the electrons from the less electronegative atom. That is what creates a transfer. We've talked about these atoms do not have brains. They do not think, hey, it'd be really fun to, hand my friend over here like a basketball. No, they're just responding to their differences in electronegativities to where that electron will actually jump and transfer over to somebody else, which is really, really, really cool. Okay, here's the key thing. So we know we are making charged ions from this transfer. It says when ions pair up to make an ionic bond, the total positive charge must balance out the total negative charge. This means that ionic compounds, even though they're made up of a bunch of positive and negative charges, will be electrically neutral. That just means their positive and negative charges will cancel out to make a zero overall charge. So here we've got some examples of ionic compounds. Guys, I think this is our first time to look at formulas and be like, okay, these are examples of ionic bonds. As you can see, I've used my colors here, right? So I got my red metal guys. Hopefully you are tracking me being like, yep, on my periodic table, those are absolutely metals to the left side of the staircase. And oh, y'all, they're bonded here with a non-metal to the right side of the staircase. Sodium chloride is an example of a metallic bond. Magnesium chloride, or not metallic, ionic bond. Magnesium chloride is an example of ionic bond. Magnesium phosphide. Oh my gosh, I'm even using words like phosphide. We're getting into it. We're going to get into naming here in a second. Okay, so we know that sodium forms a +1 charge. He's in group 1, loses that electron. Chlorine forms a -1 charge. He's in group 17, gains an electron. Well, I have one sodium atom. There's the one sodium atom with a +1 charge, I also have one chloride atom, chloride ion. I need to be saying ion, you guys. All right, there's the one, and he's got a -1 charge, right? So 1 times a +1 plus 1 times a -1, you have a +1 plus a -1, that gives you a 0. Okay, that's a very easy example. Let's bounce down here and check out what we got here. Did y'all notice there was like a little 2 underneath this chlorine? I wonder why she did that. Let's unpack this. So I don't have a subscript underneath here, which means I only have one magnesium ion, right? Got a +2 charge. But that subscript 2 means that I have 2 chloride ions. Well, each one of them has a -1 charge. Let's mathematically see how this works out to be neutral. 1 times a +2 gives you overall +2. And then 2 times a -1 gives you an overall -2. A +2 and a -2, y'all, those come together to be 0. This is what must happen in an ionic bond. You must have the same amount of negative charge to equal the positive charge. So that would require 2 chloride ions to balance out that magnesium's positive charge. I'm spending a lot of time talking about this when we're going to talk so much more about this when we name stuff. Anyway, real quick, we'll look at this last one. I got 3 magnesium ions and 2 phosphide ions. So the 3 magnesium, each with a +2 charge, and my 2 phosphorus, each with a -3 charge. This is overall +6. So this has to be overall -6. So every ionic compound, whatever the formula may be, needs to be neutral at the end. Moving on. Oh, what is the attraction? So cool, electrons are transferred. So what does that mean? What is making this force that holds the atoms together? So ionic bonding is an electrostatic attraction. She keeps making me write this word. Yes, I do, because it's important. Electrostatic attraction between the cations, positive, and the anions, negative. Once again, anytime I see electrostatic attraction, it's between a positive and a negative thing. In ionic bonds, that positive thing is a cation, and the negative thing is an anion. So this positive to negative electrostatic attraction is the bond that holds an ionic compound together. There's a lot of different ways for me to visually represent this. Y'all, oh my gosh, look, I've drawn some little Bohr model situations here. This shows the result of the sodium transferring his valence electron to where he's got a full shell underneath, satisfying that octet, lowering the potential energy, right? He's now got a positive charge. This chloride ion, oh, y'all, he's gained that guy, right? He's now satisfied his octet. You cannot see that there should be a negative charge over there, right? So it's an electrostatic attraction between this cation and this anion. Here in a more visually pleasing way, without all the dots and the circles and the whatever, I've got a positive sodium and I've got a negative chloride. And y'all, them being close to it, they're going to want to attract. That's the electrostatic attraction. This is our electron dot diagram representation. We got used to doing these in our last unit, you guys. We know that we show the cations, the metals, in this representation without any dots because they have lost their electron from that original valence shell. So what I'm seeing here is the original valence shell and what has changed within it due to the transfer, which is why that I see all 8 on here. So from the transfer, that original valence shell, which did have 7 electrons, now has 8. So it's just positives being attracted to negatives. Y'all, we ain't physically connected here at all. This is wild. What is chemistry? I know, it's exciting. Okay. Whoa. So we've transferred electrons and now we got this electrostatic attraction between positive cations and negative anions. So what structure does that create? The structure of ionic bonding is called a crystal lattice. So what a crystal lattice means is that these ions will arrange themselves in a repeating pattern so that your cations are completely surrounded by anions and vice versa. The reason for this is we know that like charges repel. So y'all, these chloride ions are not going to be next to any other negatively charged chloride ions, right? They're going to want to repel. Well, what's going to minimize that repulsion and lead to the electrostatic attraction is going to be these repeatable surrounding inserts of the negative and positives kind of interchanging, right? So each chloride negative ion is going to be surrounded by the sodium positives and vice versa. Each sodium positive ion is going to be surrounded by the negative chloride ions. Very cool. So y'all, that's table salt. Y'all are like, sodium chloride, is that table salt? Yes, it is, which we love. Okay, here's some examples of ionic bonding. I gave you some examples on that slide that we looked at, the charges must balance. Okay, so I switched to pink here just because this picture representation shows the metals as more pink than red. Hopefully you guys are following me here. So an ionic compound is between a metal cation and a non-metal anion, right? So I got sodium chloride. That's an ionic bonding. We've been using that a lot of examples on here. We've got magnesium chloride. That's an ionic bond. You're like, what is up with that too? Remember, we talked about that too. We will talk a lot more about how we get that too. And y'all are going to be like, oh, I hate this. And it's going to be okay. We'll get through it together. And here's another one. Zinc. Y'all are like, what is going on with this? This is one of my polyatomic ions. That's nitrate, which means all of those oxygens and that nitrogen collectively together pull a -1 charge. We alluded to on our polyatomic ion list that everybody that had a negative charge is acting like a non-metal. Well, here it is right here. So that non-metal acting polyatomic ion can hold in that place value and can accept electrons from zinc, which will be transferred over to it, which is really cool. Okay, so anything that's a red thing or a blue thing that we have colored so far. So the simplest whole number ratio of ions is called a formula unit. Here's the kind of sneaky weird thing that we got to kind of keep in mind is that you're looking at this, you're like, cool, 1 sodium atom and 1 chloride atom and boom, that's your ionic bond. Well, we know it's not that simple. It's a bunch of the sodium ions and a bunch of the chloride ions, and it's just a big sample of zillions of those. So when I'm writing this formula, That's the formula unit. That just shows me the ratio of how many of each ion you need to have in that entire crystal lattice structure in order for those charges to balance. Okay, so this lets me know if I were to take a sample of magnesium oxide, I would have 1 magnesium ion for every 1 oxygen ion. There would not be more oxygens or more magnesiums. They would be found in equal amounts. That simplest whole number ratio is called a formula unit for an ionic compound. Okay, so now we're gonna watch this video kind of recapping what we talked about with the formation of ionic compounds and how that leads to the structure, this crystal lattice structure of my ionic compounds.
Sodium chloride, or table salt, is an ionic compound. It exists as a lattice of sodium and chloride ions held together by strong ionic bonds. Ionic bonding is the electrostatic attraction between positive ions, called cations, and negative ions, called anions. These charges are the result of an electron transferred from one electron cloud to another. Ionic bonding occurs between metals that tend to lose valence electrons and nonmetals that tend to gain valence electrons. Sodium chloride is a compound of the metal sodium and the nonmetal chlorine. Sodium is in group 1, so it has 1 outer electron. And chlorine is in group 17, so it has 7 outer electrons. Both atoms are looking to achieve a full outer electron shell. Sodium achieves this by giving up its outer electron. In doing so, it forms a sodium ion with a 1+ charge, since it now has 1 more proton than it has electrons. Chlorine takes the electron from sodium to complete its outer shell, resulting in a chloride ion with a 1- charge, since it now has 1 more electron than it has protons. The strong attraction of the opposite charges creates the ionic bond between the ions. We can simplify this diagram to show just the valence electrons, because they're the only electrons involved in chemical bonding. As we saw, the transfer of an electron from sodium to chlorine creates the oppositely charged ions, and the electrostatic attraction of these ions is the ionic bond. This Lewis diagram shows how the valence electrons are involved in the bond, with crosses and dots to represent the electrons from each atom. Ionic bonds are non-directional, meaning they act in all directions. So, instead of forming discrete molecules, these ions attract and bond with other cations and anions to build a regular lattice of ions. And no matter how large this lattice gets, it always has a 1:1 ratio of sodium ions to chloride ions. The ionic compound magnesium oxide exists as a lattice of magnesium and oxide ions bound together by ionic bonds. It's a compound of the metal magnesium and the nonmetal oxygen. Magnesium is in group 2, so has 2 valence electrons. Oxygen is in group 16, so it has 6 valence electrons. Magnesium readily gives up its 2 outer electrons, and oxygen takes them to complete its outer shell, resulting in a magnesium ion with a 2+ charge and an oxide ion with a 2- charge. And here's the Lewis dot diagram showing how the valence electrons are involved in the bonding. The ionic bond between these ions is extremely strong due to the larger charges on the cation and anion, and these ions attract and bond with other ions to form an extremely strong lattice with a 1:1 ratio of magnesium ions to oxide ions. But ionic compounds also exist in other ratios. Calcium fluoride has a 1:2 ratio of calcium to fluoride ions in its lattice. That's because a single calcium ion having a 2+ charge attracts 2 fluoride ions, each with a 1- charge. And an ionic compound always has cations and anions in a ratio that gives a neutral charge. In this video, we've seen that ionic bonding occurs between metal cations and nonmetal anions, with the cation formed by losing electrons, and the anion by gaining these electrons. And that it's the electrostatic attraction of these oppositely charged ions that bonds them together. We've also seen how this ionic bonding results in a large repeating lattice of cations and anions.
So I love that video. It kind of recaps everything. It does a lot of nice visualization of the formation of these ionic compounds in that crystal lattice structure. It also shows like really good those ratios of those different ions needing to create an overall neutral charge to the compound. Y'all are like, gosh, Sabaga, you present the same information over and over and over again. How many times do we need to hear that cations lose and anions gains and the term crystal lattice and transfer? A lot of times. A lot of times is how many times you need to hear it, because that's how we actually retain that knowledge, by hearing the terms that define these different types of bonds much more easily. So I actually want us to kind of bounce down to the document camera and unpack a little bit more on our ionic bonding. So remember up here when it says this happens, ionic bonding, the transfer of electrons actually happens because of that large difference in electronegativity is what we wrote, right? Negativity. Spoiler alert, when I'm talking about this stuff, I'm not writing it at the same time. But we actually have, you guys, on the back of our yellow periodic tables that I gave everybody at the beginning of the year and that we use in our classroom, got a chart. We got a chart on the back. It says electronegativities of the elements. Y'all are like, oh wow, no way. Yes way, you guys. So if I'm looking at this example that we were paying attention to on sodium transferring to chlorine, and I'm telling you that they do that because of a large difference in electronegativity. Let's see. Sodium's electronegativity is 0.9. Y'all, I kind of want to write that. Electronegativity, or En equals 0.9. The funny thing is that electronegativity actually does not have a unit at the end, like joules or kilograms or stuff like that. It is just a scale on what's called the Pauling scale, which is a tangent, but it does not have a unit, so do not get freaked out about that, because you know how I'm intense on units. But this does not have a unit, so you are happy for that. And then chlorine, if I find him on my electronegativity chart. Well, first of all, y'all are like, yep, this looks exactly like our periodic table. Where are the noble gases? Well, if you remember, the noble gases don't have an electronegativity, so they are not included on this chart. If they were, that would be kind of a waste of space because they would all be zeros here. But if I look at chlorine, he's got an electronegativity of 3.2. So remember that electronegativity is how badly you want to gain electrons. And oh my gosh, he wants to gain electrons much more than this guy. So what we are looking at is it transfers over to the more electronegative atom or ion, and as a result of this, you guys, we turn into a positive charge. This one and this one is a negative charge, and that's why down here you get this really nice crystal lattice structure. I like to draw my crystal lattice structures as like a bunch of little bubblies where you have that alternating positive negative, right? To where all of the negatives only touch positives and all of the positives only touch negatives. That's the crystal lattice structure. It is not two-dimensional like my drawing. It is more 3D, like this little cube section right there. And then I kind of want to unpack on our examples, like what we talked about on the slides, okay? We said that the number of each type of ion is given depending on what is required in order to create a neutral charge, the same amount of positive as there is negative. So in each one of these compounds, I see the metal written first, right? And then I see the non-metal written second. So when we did our coloring up here at the top, I was like, yeah, metals, they always go first. Well, here I'm actually seeing that the metal is written first. And remember, nitrate, he's on my list of my polyatomic ions. Remember we said my polyatomic ions. Where is he? There he goes, right? He overall has a -1 charge, so he is acting non-metal-like, which is why we will write him behind zinc in a compound. Okay, so we got sodium. We know sodium has a +1 charge. Why? Because he's in group 1. Chlorine, he's got a -1 charge. Why? Because he's in group 17. So that's why I only have 1 to 1 of each one of those things. Got 1 positive charge, we'll cancel out 1 negative charge. Moving on, magnesium, group 2, +2 charge. Chlorine still got a -2. Well, this is why I need 2 chlorines to cancel off that overall positive 2 charge from magnesium. I need to create an overall negative 2 charge. So that's why there's 2. And then zinc, you're like, great, zinc on my periodic table. Y'all, he's in the transition metal. He's not in one of my fancy groups that she made me write numbers on the top. No, he is not. But I did have you guys write this on your colored periodic table that zinc always has a +2 charge, which is very exciting. And then you're like, what are you talking about with this? There's lots of things here. That is not lots of things. That is just a nitrate. And if you'll remember nitrate, he has a -1 charge. So he's all in parentheses because he's acting as one thing. And I got 2 of him because I gotta have 2 -1 charge things to balance off zinc's -2. So it was a little bit of a tangent, so I thought we kind of unpack that a little bit more because also I just kind of like talking about this stuff because I'm weird and a nerd. Okay, let's move on. Okay, what is the relative strength of ionic bonding? In our intro, we did metallic ionic covalent, so that puts ionic bonding straight in the middle. They are the 2nd strongest bonding type. And it's pretty strong because of that strong electrostatic attraction between the 2 ions. And it's hard to disrupt. When I say disrupt, I mean move them around or cause that separation that is created from them wanting to be together. Okay, as a result of being pretty strong, ionic compounds have some really interesting properties. We're going to talk about melting points. Y'all, they're going to be high. And boiling points are going to be high. It's going to take a lot of energy to disrupt that electrostatic attraction between those ions in order to overcome that attractive force to move and separate the ions. So y'all were like, well, when we did metallic bonds, she said it was high and high then too. And I did. Ionic compounds, because they are technically stronger overall than my metallic bonding, when I say melting points are high, they're higher also than metallic bonds. Boiling points are higher than metallic bonds. So here are some examples here. Y'all are like, whoa, some big numbers. Well, Kelvin is a different representation scale of temperature. But what this would equate to in Celsius is probably like 800 degrees Celsius or like 700 degrees Celsius, okay? And you're like, wow, that's pretty high. What were the temperatures for my ionic bonds? They were like in the 100s, 200s, 300s. So already I've got really higher melting points. And y'all are looking at this and you're like, you're telling me that table salt will require more energy to melt than like copper? Yes. Which is wild. That just means these cations and these anions are even stronger attracted to each other than the metal cations and then the delocalized electrons that we would see from metallic bonding in that sea of electrons. Okay, I got some ginormous boiling points. Boiling goes from a liquid to a gas. That is wild and crazy and looks like it is not on planet Earth able for us to reach those temperatures. Okay, so melting point high, boiling point high. Moving on. More properties. Ionic compounds, hard. You're like, yep, that makes sense because they're real strong. Yeah, so electrostatic attraction makes a very rigid crystal structure that resists deformation. And then here she's giving me this word brittle. You're like, wait a minute, I thought you said it was hard. Brittle is the opposite. Brittle is not technically the opposite. Brittle just means that the layers of an ionic sample can shift. And let's think about what happens when these layers shift. So here's a nice little picture. I have hammered my ionic compound and I've caused it to shift. Uh-oh. Now I've brought 2 light charged ions into contact and you better believe they do not like that. As a result, they will repel. And that's where you get that shattering. That is the term brittle represents. So under stress, yes, it's hard, but when I stress it, the layers will shift and they will shatter. That is what a brittle definition is. Okay, state of matter, y'all, they're solids usually at room temperature. Solids, if you think about it, are packed together. I'm telling you that ionic compounds are very strong. That means they're probably also going to want to be close together, which is why they are typically solids at room temperature. Okay, let's talk about conductivity. So conductivity is a big topic that we are going to hit each one of my 3 bond types. You guys, we said metals are always conductive. Great. Conductive of heat, electricity, all of the things. We love that for them. Ionic compounds is a little bit different. It depends on what state of matter I am in. So ionic compounds are good conductors of electricity only in the molten state or when aqueous, which means dissolved in water. You're like, what is going on with all these letters in parentheses? Molten means liquid, okay? That what you were seeing here is a L. I know it looks like a 1. Work with me here. That font was not the best choice. It's an L in parentheses. And if I want to represent something that is in the liquid state, I would put that L in parentheses right next to that ionic compound formula. That just lets me know it's in its liquid form. Now, aqueous. This is a weird term. I say aqueous because I'm from Texas. Some people say aqueous. I feel like I would have to work too hard in my brain to say aqueous, so aqueous just kind of falls out a little bit more naturally. But if I'm saying something is aqueous, it means it's dissolved in water. So like think about me dropping sodium chloride into water and stirring it up. Okay, I would say I have an aqueous sample of sodium chloride. Salt water is aqueous sodium chloride, okay? But to let you know that it's dissolved in water, you will see a AQ symbol following that formula. Okay, let's just get to these pictures. So what is she talking about? So here is molten or liquid form ionic compound, and here is a aqueous form of an ionic compound. If you can see little Mickey Mouse guys, that means that these ions, the positive and negative ions that are from that ionic compound, are now in water. Him in its liquid form, there is no water in there. Do not think that water is the only liquid. Anything can be a liquid if I get to melt it at the temperature at which it melts at. So this is just now fluid ions from my ionic compound. So melting, which is liquid, and dissolving, which means dissolving in water. Why is this important? It says if it is molten, y'all, the ions can move. And it says if it is dissolved, the ions can move. Well, this is exciting. So this creates how they can conduct, you guys. When I drop them in water, specifically the aqueous version of an ionic compound, I drop them in water. That means that the ionic compounds can dissociate, okay? This is a unique thing that ionic compounds do, okay? Dissociation is when ionic compounds will break down into their ions, and each ion is completely surrounded by water molecules. You're like, well, how does that happen? We said that attraction is real strong. Yeah, but you know what is also real fun about water? You'll probably have heard the term water is polar. We will get into that next semester. But water's got like a negative end part of him and a positive end part of him. And he's real strong, okay? So when sodium chloride drops in the water, those water molecules separate them and surround them, okay? So that's what it means to dissociate. So going back up here to my picture, if you'll notice, I wrote ions can move. Ions can move. I guess movement of ions is what is important for being able to conduct electricity. Okay, let's see. Yes. So the reason why ionic compounds can conduct in liquid state or when they are dissolved in water, aqueous state, is because now those ions are free to move. They are mobile. And if I've got mobile charged particles, I can transfer electrical charge. So what we are looking at here is a picture of an electrical field. I've got a negative electrically charged plate. I've got a positive electrically charged plate. Those ions, they be mobile, you guys. So that means my negative guys can travel to the positive end, and my positive end can travel to the other end. And movement of negative and positive charges can now conduct that electricity. So the key thing here is they've got to be able to move. Okay, so let's talk about this. Have y'all heard the term electrolyte? Ionic compounds are also called electrolytes. The electrolytes are substances that do this dissociation in water and create these mobile ions when they are dissolved in water. Y'all are thinking Gatorade. Yeah, y'all, Gatorade has ionic compounds in there. A lot of Gatorade is made up of water, so when those ionic compounds are put into that Gatorade mix, they exist as these mobile ions, yeah? Those mobile ions, they're good for your body, also good for conducting electricity, you guys. I can actually do this. I can stick my electrical circuit into a sample of dissolved salt water, and y'all, that light bulb's gonna light up bright, okay? Because I've got ions that are mobile, able to conduct that electricity, which is really exciting. We'll talk about examples of non-electrolytes, but some compounds do not conduct electricity. This is not an ionic compound. Y'all are like carbon, hydrogen, oxygen, that's non-metals. That we'll learn about for covalent. This is covalent. But ionic compounds, they dissociate like this. They conduct electricity. We call that being an electrolyte. So we are all into this mobile ion stuff. Great, mobile ions, mobile ions. So if that's required to conduct electricity, what state of matter would not do a good job of being mobile and conducting electricity? solids. So ionic compounds, they great at moving and conducting electricity when they are liquid and they are aqueous. They are awful at conducting electricity when they are solid. Why? Ionic compounds, y'all, they got that super strong electrostatic attraction, which causes that rigid crystal lattice. Therefore, your ions, they're not going to be mobile, and will be unable to transfer that electrical charge. So here's a solid. We know that solids, they stuck together, just vibrating, not moving. Well, they can't move to the ends of the poles that they're trying to get to. Electricity cannot be transferred. Okay. Now, before we watch this fun video, which I am excited about, I thought we would kind of maybe break it down a little bit in terms of this conductivity. Y'all are like, oh my gosh, she keeps talking about this conductivity thing. And I'm like, yes, I do, because it's important. I made myself a chart that I thought I would share with you guys. Here's a chart. I've got my metallic bond, and I've got an ionic bond. I also have visual representations for you of what this structure. So here's my sea of electrons, right? With the delocalized electrons here. And here is my crystal lattice of ions, right? For my ionic bond. Now, metallic bonds can always conduct electricity because they got mobile, delocalized electrons flowing all the time, all states of matter, right? But my ionic bonds, we just talked about, they only conduct electricity when they are in their liquid form or in their aqueous form. Only then are the ions free to move. Here's the key thing about both of these. Mobile. Anything that is mobile, a charged negative particle that is mobile will conduct electricity. Now, what that charged negative particle is different here. My sea of electrons is an electron. Just a little electron moving around. In my ionic compound, either in liquid or aqueous form, it's an entire negatively charged ion. So the key thing here is to conduct electricity, you must have mobile charged particles. In metallic bonds, it's electrons, and in ionic bonds, it's ions. Okay, so that was like a giant little tangent, but I like the pictures and I like the breaking everything down. Okay, so I think this is when we're about to get into nomenclature. So I was about to be like, we're done. We're not quite done yet, but I do want to show this video that relates how this structure of the crystal lattice and these ions create all these fun properties that we just discussed.
Many ionic compounds do not just exist in a laboratory or in your chemistry homework. Sodium chloride is regular table salt. Sodium fluoride is added to some toothpastes to help strengthen tooth enamel. Ammonium nitrate can be used to fertilize plants. Although their real-life applications are very different, they share a few key properties. In this lesson, we will learn about the properties of ionic compounds. These ionic compounds have very high melting points and are brittle because of their 3D giant ionic lattice structure. The strong electrostatic attractions holding the 3D lattice structure in place mean that a lot of energy is required to overcome these attractions. When we apply a force, it breaks the regular repeating pattern of oppositely charged ions, causing ions with like charges to come close to one another. The ensuing repulsion breaks the lattice structure. Sodium chloride, sodium fluoride, and ammonium nitrate can all dissolve in water, as we know. Or else we wouldn't be able to flavor our soups, brush our teeth, or fertilize our plants. Most ionic compounds are soluble in water. In water, an ionic compound can dissociate into its ions. So when we dissolve sodium chloride, it will dissociate into sodium and chloride ions. These ions become stabilized in water due to the polar nature of water. As you can see, the sodium ions are stabilized by the negative dipole of water, and the chloride ions are stabilized by the positive dipoles of water. This solvation stabilizes the free-floating ions. An ionic compound dissolved in water can conduct electricity. This is another key property of ionic compounds. This is made possible due to the presence of free-floating ions. We can dissolve copper 2 sulfate in water in a beaker. Add a few drops of sulfuric acid. Place a strip of copper and a strip of zinc into the solution. These will act as electrodes. Using 2 alligator clips, connect one strip to one end of the mini light bulb and another strip to the other end to complete the circuit. You will see that the light bulb lights up. Hence, the solution conducts electricity. Following on the same idea, molten ionic compounds can also conduct electricity. The lattice structure is broken at high temperatures, and so the ions become free-floating. In summary, ionic compounds have high melting points, are brittle, and can conduct electricity when dissolved in water or molten due to the presence of free-floating ions.
Y'all are like, oh my gosh, she's repeating the same information over and over again. And I am. Yeah. So the main thing to keep in mind is these ionic compounds, really, really, really strong, high melting points, high boiling points, good conductors, but only good conductors when they're liquid or aqueous. Now, before we talk for that little blip on the bottom of our notes page about nomenclature, I thought we would come back down to our actual notes page and maybe add a few things here, specifically when it comes to this conductivity section. So what we're looking at here is we have a sample of an ionic compound, and we said it can conduct when it is liquid and when it is aqueous. So I want us to actually kind of label these pictures. This is liquid and this is aqueous, right? And as a result of when they're liquid or aqueous, they can move. So here is also a really nice picture showing how sodium chloride will split up into its ions because water actually breaks that electrostatic attraction and surrounds those two ions completely. So this is called dissociation. And I know it says dissociation up here in your notes, but sometimes I like to write the words next to the picture. So when I see the picture, I'm like, okay, yes. Okay. And this is what happens when we are aqueous, okay? So now we zip on down here, and this is showing a solid guy. Solids do not conduct electricity, so we're going to write no mobile ions. So there are no mobile ions when I am solid. And over here, we are going to write mobile ions. So these are showing some mobile ions in molten or aqueous solution. So we're going to write liquid or aqueous. Yes, it's a nice little picture right here showing the visuals. And you know I like my visuals. So hopefully that'll make it a little bit more warm and fuzzy feeling inside, kind of gathering all that information. Okay, we're going to spend like lessons upon lessons of nomenclature, but I'm going to real quick do a little intro. I'm sorry if I'm going fast. Today is not the day to learn nomenclature. Today is the day for us to just get through the notes. So that is what we are doing right now. So let's talk about subscript numbers. So when I'm talking about subscript, I'm talking about the teeny tiny numbers that are dropped down below. That tells you how many of each ion or atom you have. So from a formula like this, I can see that I have one calcium atom and one or two chlorine atoms. And in fact, I think I have the answers here. Let's just talk. Yep. One calcium atom and two chlorine atoms. If you do not see a number, that means there is only one representative of that atom or ion. Zipping on down here gets a little bit freakier. I don't see any number underneath iron, so there's one iron. Now here's where it gets weird. Originally, I did not see a number underneath manganese here, but this whole structure, this polyatomic ion permanganate, has got a 2 outside of the parentheses. That 2 does like the distributive property, like in math class, where that 2 gets distributed to every element on the inside of that parentheses. So that means I actually have 2 manganese atoms. Oxygen atoms. Oxygen inside of here has a 4. Well, that 2 gets distributed into the 4, so 2 times 4 gives you a total of 8 oxygen atoms. Now, I can also ask about how many of the entire permanganate polyatomic ion. Well, the subscript on the outside of that entire polyatomic ion, that too tells me I have 2 permanganate ions. Okay. Now, Oxidation number, oxidation number, oxidation number. It tells you what the charge is of each one of your ions. We got these numbers on our periodic table. Hopefully a lot of them are committed to memory. Main thing is that, y'all, if we a transition metal or if we are a metal underneath the stairs, not even necessarily in the D block. I'm talking about tin. I'm talking about antimony. I'm talking about arsenic. I'm talking about lead. These guys and the transition block will all have varying charges. But we know our arrow that goes +1, +2, +3, showing that silver has a +1 charge, zinc always has a +2, and aluminum always has a +3. Anybody else in this D block or underneath this staircase, we do not know. That just means my only metals that I am confident on knowing their charge are just group 1 and group 2. You're like, oh my gosh, well, how am I supposed to figure this out? Well, this is why we have rules in my nomenclature booklet. Okay, I'm going to zip through these rules like super quick. We are only focusing on the ionic naming and writing formula side. Ionic naming, meaning if I were to give you a formula, you would be able to tell me the name of the compound. We're going to name the cation, which is the first guy, the metal. If you are in group 1 or group 2, silver, zinc, or aluminum, or if you're the positive polyatomic ion ammonium, you just name whatever that thing is. Silver, zinc, ammonium. If you got another weird transition metal, like I said, the ones in the D block are under the staircase, you got to name the element, and then you got to put a charge in Roman numerals and parentheses. Y'all are like, what does this mean? We will get to it. Now that I'm naming the anion, the second element, the nonmetal, if it is a single nonmetal element from the periodic table, just name it. But we're going to change the ending of that nonmetal to "ide." If your second anion is a polyatomic ion, we said on our list of polyatomic ions, there are a bunch of them with negative charges that are acting like nonmetals. If I've got one of those, I just name whatever the polyatomic ion is. So here are my examples. I've got sodium. Sodium's in group 1, right? So I just got to name him. Sodium. Great. Moving on. My next guy. I got oxygen. Oxygen, oxygen, oxygen. He's just a single element. So oxide. Some of y'all are freaking out here about that too. You're like, what about that too? What about that too? Do not freak out about that too. Use the rules. Just name the metal and the nonmetal and move on with your life. Second example is a little bit more of a complicated one. So my first cation, my metal, is iron. Oh no, he's in the D block, which means I need the charge in Roman numerals in parentheses right after him. So this is iron 3 sulfate. That 3 means that this iron has a positive 3 charge. You were like, how does she get that? I'm going to talk real fast and then we're going to unpack this in class. But that 3 on the outside lets me know that I need 3 sulfates to accommodate for iron's plus 3 charge. So that 3, I think about doing a reverse zipping up and saying that that iron, we know it was found on the opposite anion, which means that his charge must have been a plus 3. And then my second guy is not a nonmetal from the periodic table. It's one of my polyatomic ions. I would recognize that from my list as sulfate. So this formula is iron 3 sulfate. So this is a little bit tricky, which is why we are going to spend a week practicing naming these things. Now I can do the reverse, writing a formula, which means I've given you the name of the ionic compound and you can create a formula for me. And the symbol or the strategy behind this is something called a crisscross. So I'm going to write the symbols for the ions. Let's go ahead and focus on one of my examples to explain more what I'm talking about here. So I'm going to write my symbols, right? So for magnesium, I know magnesium, there he is, Mg, and he's in group 2, so we know he's got a +2. So I write the symbols and the oxidation numbers, right? And then chloride, that means chlorine. There he is, Cl. He's in group 17, so he makes a -1 charge. So I've established the symbols with the oxidation numbers, and then I crisscross. What that means is I take the numerical value of that charge, not the positive or negative, and that gets slammed down to the opposite ion as a subscript. So that 2 from magnesium goes to 2 chlorides. And fluorine has 1 -1, yes, but I'm just taking the number, not the negative or positive sign, and that gets slammed down on magnesium. So that is a fancy way of giving you the formula unit of an ionic compound, which is that lowest whole number ratio to neutralize the positive and negative charges. So I've crisscrossed those charges down. Boom. Those become the subscripts. This one's a little bit trickier. Oh my gosh, copper. What is that 2? That Roman numeral 2 tells me that that copper has a +2 charge. Y'all, Remember we said the transition metals, we don't know, they got variable oxidation numbers. I could have a copper with a +1 charge. Here I am telling you that it is the copper with a +2 charge. And I've given you that information in Roman numerals. We love that. And then I have sulfite. Sulfite is a polyatomic ion. It is SO3 with a -2 charge. So here I've written the symbols and the oxidation numbers, and then I crisscross them down. Boom. So here, yeah, everybody gets a 2 from the opposite guy. But here's my last rule. I can reduce those ratios of the subscripts if needed, which means that 2 and that 2 I can reduce down to a 1-to-1 ratio. By definition, ionic compounds formula units is the lowest whole number ratio of each ion to each other in a crystal lattice. Saying I have 2 copper ions for every 2 sulfate ions is the same thing as saying it is a 1-to-1 ratio. I feel like I talked longer about that than I should have, but we're gonna do this all in class. So I'm very excited to see you guys next time to talk about nomenclature and practice writing compounds and naming formulas for these ionic compounds.